All right, recording is rolling. It's Friday, September 1st. So my projection is broken just for context. Just watch this video at home. We're just going to do a couple of things today. One thing, I've got a ruler or a ruler activity. Right? You guys got rulers in your desks, right? Right, so we're going to do activity set. Right? And then I'll give you guys the rest of the class time after we do this activity to work on these puzzles that are going to be due Tuesday. Right? You guys remember these are due Tuesday, right? Okay. And actually, I will help you out with one of these scenarios. The very last scenario. You guys get to number 1920 yet? Number 19, number 20? There's a little bit of a trick with that one. So that'll be later in class today. But let's start with these rulers. All right, now the deal with the rulers is you have you guys get into partners. Get into pairs. Okay. Suppose my two hands are two different people. Right, so my right hand's one person, the left hand's a different person. Right, I got Alan and Bob on it, and I'm holding the ruler like this. Notice my left hand is right at the 0 centimeter mark, right? And I let the ruler fall, and then I catch it as fast as I can. Right? Well, while the ruler is falling, guys, is it falling at constant what velocity or acceleration?
Acceleration.
Acceleration, constant acceleration, right? About 10 meters per second squared, right? So it's speeding up. It's just speeding up at a uniform rate. Right? Hey, if you knew how far it fell, I mean, that's the purpose of rulers, just tell you something about distance, right? Suppose you catch it at the like the 21 centimeter mark, right? So I catch it at 21 centimeter. Is that going to correspond to some falling time? Ooh, do you think you could calculate your reaction time based on how far the ruler fell? Ooh, you guys see that? Right. Give you guys a little bit of a hint here. You guys see these three kinematic equations? Where's my, man. I was gonna have them for the video, but well, the pause this real fast. All right, here we go. Recording resume. Found them. Right, so these three kinematic formulas right here. You guys see these, right? Probably a good idea to memorize, but I guess well, I won't make you guys memorize them, but if you want to get pretty good at physics, that's probably a good idea. Right? Now, which one of those, the first, second, or third, tells you something about the relationship between how far the ruler would fall and how much time it took to fall that distance? What do you think? Yeah, the top one, the first one, right? Because the first one is the only one that has both x and t in it. See, the problem with the second one is it doesn't say anything about falling distance, right? And the problem with the third one is it doesn't say anything about falling time. So it's probably some version of the first one, right? So I'm going to give you guys a couple of minutes. Go ahead and try it out with each other. So pair up, drop rulers, catch rulers, and I want to see if someone can come up with a reasonable reaction time. So go ahead. And pause recording. All right, recording is resumed. All right, so you guys been working on this a few minutes. Just everybody had at least a fall distance, like the ruler fell some distance. So you see the marking you caught it at. All right. So I know you guys in class can't see what I've got on this projection. This is really just for the video, but you can see what I've got here on the whiteboard, right? Is this? Right. Now, you guys told me already you want to use the first kinematic equation, right? The first one. Right. And anytime you drop the ruler, what is initial velocity equal to? 0. So you can just get rid of that bit right there, right? You can get rid of this v dot t. It just goes to 0 anyway. And that just simplifies it to x equals 1/2 at squared. Is that? Hey, x equals 1/2 at squared. Where did you guys see that before? College, right? That's a college equation, isn't it? College, right? Here. So up here on the board, I amended it a little bit. Right, so we got the simplified version, and instead of x for just so general, just kind of put h for like a fall height. Okay. For the acceleration, I got acceleration due to gravity. That can be called g, right? Okay. And you guys are trying to calculate your reaction time, right? Like the fall time, based on knowing how fast it's going to speed up in Earth's gravity, and also how far it falls. Right? Can you guys do the algebra and solve for t in terms of h and g, like the fall height and the Earth gravity? Can you guys see that? You guys see that? Right? And then, since you know how far the ruler fell, could you just plug that in for what? How far the ruler fell? That you're going to plug that into which variable? Yeah, x or h, x or h, right? You can use those for displacement. And so how about now? Who's got a reaction time that looks pretty reasonable? You guys still working on that? Oh, what? 0.2 seconds? 0.2 seconds? All right, 0.2 seconds. All right. Yeah, that actually is about the average human reaction time, about 0.2 seconds. There's one more thing I do want to mention. I didn't know if you guys were gonna get tripped up by this, but it sounds like you guys got this right. Suppose you catch the roller at 21 centimeters. Suppose it falls like 21 centimeters. Just make up a number. Okay? Do you want to plug in for H the number 21? Yes or no? And why? Right, but see, okay, if you got a reaction time of 0.2 seconds, that sounds correct. So, which means you didn't actually plug in like 20 or 21 there. You plugged in. Well, here's what I'm trying to get at. The roller falls, and the markings on the roller is some number of centimeters, right? But gravity field, what have we been using for gravity field? Yeah, about 10 meters per second squared. You use 10 meters per second squared, right? Yeah. Do you guys see there's a discrepancy in units? Like there's centimeters on the roller, and there's something to do with meters in the gravity, right? Like meters per second squared, right? So it all has to be same unit. Like if you plugged in the number 21 for H 21, what you're saying is that like 21 of these meter sticks fell through your hands. That's what you're saying. If you plug in 21 for H, you say like 21 of these, right? Which would be like a really slow reaction time. So guys, 21 centimeters, how many meters is that equal to? Guys, what does centi mean? Centi, how many cents on a dollar? So it's 100, right? Right. So if I have something like 21 centimeters, suppose I caught it at 21 centimeters, right? The number actually feed into this equation for the drop height is not 21, it's what? 0.21. 0.21, because that's in terms of meters. So that meters here cancels with the meters as in the meters per second squared here. You're gonna get seconds out of that. Right? You see that? Right. Give you guys one more shot. All right. So now that you guys know to convert centimeters to meters. Okay. Go ahead and see if you can get your reaction time. So here, might be some like where the H is, I'll just put 0.21 if I caught it at 21 centimeters. Where the G is, yeah, you can put, yeah, there you go, 10 right, meters per second squared. Speed meters per second squared. Yeah. Right. Yeah, and again, yeah, you should get a reaction time about what Alexandra got, right? About 0.2 seconds. Okay. Right, you guys get that? All right. Next thing, I do want to give you guys time and class to work on these puzzles, right? The pages boxes on it. You guys that? When am I picking up this page with the boxes on it? Tuesday. Good call. So it's coming back from the 3-day Labor Day weekend. You guys know we got a 3-day weekend coming, right? So last class, students had a question about the very last scenario. So I want to give you guys a hint about the very last one. Because all those other scenarios, you can pretty much just use the 3 kinematic equation to plug stuff in and then figure out stuff from there. But the very last scenario is a little bit tricky. Okay? It's the one that says a car brakes to a stop. It takes the car some given time and displacement to come to a stop. Find the acceleration. That's to say the rate the car is slowing down in this case. And also the speed of the car just before he started braking. Now, the reason that is tricky is like if you make a checklist of variables, okay, you have, here, I told you guys the braking time, I told you guys the braking distance, and the fact that the car is coming to a stop, what do you know about final velocity? Yes, it goes to 0, right? And I did not give you the rate the car slowed down, that's acceleration, or the starting velocity of the car, that's v naught. Okay? So from an algebra point of view, the reason that's tricky is because A and V naught would be 2 unknowns in the first equation. So the first equation can't get it by itself. Guys, can you solve one equation with 2 unknowns in it? No, the best you can do is come up with like a graphical relationship, but so that won't get the answer. The second equation has the same problem. It's got the V naught and the A in it. The third one also has the same problem. Like all 3 equations have the V naught and the A. You guys see that? Which means that no single one of those equations can solve this. So there's two ways you can solve this, or at least two ways I'm going to show you guys. Two ways to solve this. Right, one way you can solve this is by setting up a system of equations. Right? So that is over here on the whiteboard. Right? So I've got two different audiences here. If you're watching this video at home, I got this on the paper. If you're in class, I got a system of equations here. Now look at this. X equals v naught t plus f at squared, where I'm trying to solve for the v naught and the a. Df equals v naught plus at, where I'm solving for v naught dA. Ah, you guys see that? Right. Oh, if you have two independent equations with two unknowns, is that solvable? That sure is. That's why that's a system of equations. Now, how do you solve that? Well, that's where you go to, you guys remember like substitution versus like elimination? You guys remember stuff like that? You can even solve it with the matrix possibly. Okay. So I did like a substitution method here. So well, v naught, let's equal this. This circle version is just this bottom one rearranged. You can substitute this v naught up in here, and then solve for a, like the acceleration. You can get that way, right? So you can solve this scenario with a system of equations. Is that okay? Right. But actually, there's another way I like even more than that, and that's to solve it with a graph. You guys see this graph up here on the whiteboard? See the graph? Right. Oh look, it's a v versus t graph. You guys see it's velocity versus time? Sure, let me straighten this out a little bit. This is supposed to be a straight line. I'm gonna make this straight line as I can. I guess that's pretty close right there. That's about a straight line, right? Okay. Right. So the car, oh, and yes, car braking to stop. Isn't that exactly this poster right here? Car brakes to stop. Right. You guys see the one that says V versus T? Right. That's just bam, it's blown up right here. Ah, so velocity versus time for car braking to stop. Right, you guys see it? So at time 0, the car was moving with some initial velocity, and then after some time t, which is 0, came to stop. Is that right? Now you don't know. Okay, here's what you do know. You do know how much time. You also know. Wait, what else to give you? Final velocity, obviously. You know final velocity. You know how much time, and you know the braking distance. Right, guys, on a v versus t graph, what property could tell you the distance that the car went? What property tells you the distance that the car went? Okay, yeah, x. Okay, but if we're looking at a velocity versus time graph, does x is that going to be a coordinate, a slope, or an area? The area, right? Is it the area under a v versus t curve equal to like the displacement? Right? Okay, so now you can bring out some triangle geometry. You could say, here I've got it right here. But I'll go ahead and right here for the video. Right? That the distance the car went, x. Right out here. X is equal to area of a triangle, 1/2 times base times height. And since you know the braking time, you have the base of the triangle. You don't know the height of the triangle, but you do know the area because I told you the braking distance, right? So you guys see you can solve for that initial velocity? You guys see you can solve for initial velocity? Right, you guys see it? Right, is that okay? Okay. And then once you have initial velocity, the other question is, what's the acceleration of the car? In this case, it's going to be a negative acceleration because the car's slowed down, right? And what property on a v versus t graph tells you acceleration? Is that a coordinate, a slope, or an area? The slope, right? Because that's the rate change of velocity. That's what acceleration is. In fact, it's downward sloping because it's a negative acceleration. The car's slowing down, right? Now, at this point, you'll know what v naught is because you solved it using the geometry of the triangle. Okay? Area, right? And since you know the braking time because I gave that to you, you do rise over run, and you can solve for the acceleration of the car. Okay. Okay. You guys get that? Okay. So yeah. So just to recap, all those boxy page looking puzzles. There. Right. Most of them you can just plug into the 3 kinematic formulas, set up equations, and just solve them that way. The very last scenario that involves the car braking to a stop, that was a little bit tricky. And I just showed you guys 2 ways to do it. You can either set up a system of equations, or you can set up a v versus t graph and use the geometry of a triangle. Okay. You guys got that? All right. So yeah, I know today's a kind of weird day and projection not working. So I'm gonna give you guys the rest of today to work on those puzzles. And if you have any questions, let me know. Otherwise, I'm gonna just go ahead and end this recording.